Hi, this is a presentation of our second project video for ECEN 452 for group number 2. We had earlier demonstrated how we went through to create an image using MATLAB. So at this point, we're going to go a little bit through what happened when an image is processed, and I'm just going to read through here. And I believe that at the end of this presentation, we're going to learn something from it. And so BPSK can be considered as a form of amplitude shift keying, where each non-return to zero data bit of value 0 is mapped into a -1, and each non-return 0 1 is mapped into a +1, where the resulting signal is then passed through a filter to limit its bandwidth and then multiplied by the carrier signal cos omega t. Now, BPSK it simply means that the phase is shifted forward by 180 degrees for a 1 bit in the data and left unmodified for a 0 bit in the data. Don't let this intimidate you. This is just the polar coordinate system that we have been studying in the past, with each x representing the modulation of the carrier of each bit. Notice that the distance from the origin A is always 1. With that said, we should keep in mind that BPSK does not use amplitude modulation at all. The modulating signal, however, is not just the stream of bits that make up the frame. Additional work goes into prepare the incoming bit stream for transmission so that it will better survive the sometimes nasty conditions of the radio frequency channel. Each incoming data is mapped to 11 transmission bits. These outgoing 11 bits are called together one symbol, and each of the 11 bits is individually called a chip. The process of mapping bits into chip is known as spreading. The term derived from the effect the mapping has of spreading out the frequency range that the signal takes on. Or one can think of the process as spreading the information contained in the original data bit over the various chip bits of the symbol. This expanding of one data bit to 11 chip bit is done to protect the signal from various types of interference. And the mapping is very specific, a sequence known as Baker sequence. The sequence used is as follows, where you have the first bit is always a +1, the second bit -1, +1, +1, -1, +1, +1, +1, -1, -1, -1, where +1 represents the 1 bit and -1 represents the 0 bit. This sequence might seem to be random, but it was chosen because it possesses an important real-world property. As the signal encoded with this Baker sequence reflects off surfaces, it will be delayed a bit relative to the original signal. And each delay reflection that hits the receiver will appear to be added together, causing the received signal to appear blurred out as the sequence overlap. And as we can see this in this image, this process image, it looks very blurry. Let me see if I can enlarge it. It looks very blurry. As you can see, the receive image looks very blurry because information is added to it before it's transmitted. And the reason for doing this is just to help protect the real the real information that is transmitted. Um, and so going forward, so the important mathematical property of the Baker sequence is that the autocorrelation, or the sum of the element-wise product of the sequence and any delayed version of the sequence, will have a strong peak when no delay is present and will be close to zero otherwise. This allows the receiver to use math to hunt out the main signal, and we can see this here in ways using math to hunt out the received signal. So it says if I equals 1, then n, and then if string in add inputs I equals 1, then a of I equals 1. Else, if it is negative 0, then you end it, which you can see again from the explanation. The first bit is usually 1 and the last bit is usually negative 1 in my understanding. So if we go back to here, it says the part that comes directly from the transmitter and not off the reflected surfaces, and filtered out the, the, the echoes to get a cleaner signal. Furthermore, the increasing of the rate by a factor of 11 provides redundancy in time, which causes spreading in frequency to the final 20 megahertz bandwidth. The advantage of spreading the signal over a wider range of frequencies is that many interferences sources are narrowed band and will then affect only a small part of the encoded signal rather than the entire signal, and the receiver may still be able to recover the original data. And so again, if we go back to these, you can see how our received signal is really blurry. I had a 3D picture of the United States map, and it's right here. It's not. It's here. You may not be able to see it very clearly, but this picture is so bright and beautiful. But when I process this picture, it could not come through because of the internal mathematics that is taking place inside the process of transmitting and receiving this image. And so if you transmit this particular image of the American map, it's going to take forever and it's not going to return anything because the picture is a 3D in 3D format. It really has heavy colors and it's going to take forever to process it given the math that is going on in the in the program, in the code. And so this brings us, group 2, to the end of our presentation. And so far, this is what we've been able to achieve as a process image using the code, as you can see here. And thank you so much for listening, and do have a great rest of your day.